In this first part of Chapter 1, we're going to cover organic chemistry and do a quick review about atoms. So first off, organic chemistry is the study of organic compounds. It seems like a very narrow branch of chemistry, but it's actually a very vast area of chemistry when we talk about what organic compounds are. Organic compounds are any compounds that are composed primarily of carbon and hydrogen. So carbon becomes very unique for organic chemistry. So let's review a little bit about carbon. Carbon can form 4 covalent bonds. So this allows for carbon compounds to either be linear or in branch structures. So what we mean by that is since carbon can actually form 4 bonds, we can take one carbon atom and we can connect it to another carbon atom, and we can continue on in this linear type fashion, making sure that each one of those carbon atoms has 4 bonds associated with it. But all these carbons are connected in a linear fashion. With those 4 bonds, though, we can also make it connected in more of a branched fashion. So I can take one carbon atom and attach it to the next, and then I can attach a third carbon atom as well, but then I can make one of the other carbon atoms coming off the middle of that initial chain. So this is what we would talk about as a branch structure for carbon. And this is what makes so many different organic molecules, is because of the ways that we can attach carbon, since it can form 4 covalent bonds. Carbon can also form single, double, or triple bonds. So this allows us to put a variety of different bonding patterns in our structures as well. So if we just look at an example of a linear structure of carbon, I can connect 2 carbon atoms with a single bond, but then I can also use a double bond to connect carbon atoms as well. From that double bond, I can then also have carbon have a triple bond associated with it, which will continue along the chain, giving me different patterns and different arrangements for all of those different carbon atoms. What you do want to recognize that even when we have our double or our triple bonds, we still only have 4 bonds connected to our carbon atoms. Carbon also forms very strong bonds with both itself and with hydrogen, which is one of the reasons why we have so many carbon-based compounds. So just to give you an example here, a carbon-carbon bond is about 339 kilojoules per mole of energy, where silicon, which is directly beneath carbon on the periodic table, if we bind 2 silicons together, is only 223 kilojoules per mole for the energy. So carbon-carbon bonds are very strong in comparison to other atoms in the same group. We can look at the same scenario with a carbon-hydrogen bond, and you can see how much stronger a carbon-hydrogen bond is compared to a silicon-hydrogen bond. So this is another reason why we have so many different compounds associated with our carbon. So let's quickly review our atomic structure. So all atoms contain a nucleus, and in that nucleus we have protons and we have neutrons. Remember, protons have the positive charge, and neutrons are neutral, or they do not have a charge associated with them at all. In the nucleus accounts for most of the mass of the atom. The protons and the neutrons both have a relative mass of 1, so this is the massive part of the atom. The nucleus is about 10 to the 15th or to 10 to the minus 14th meters in diameter. So it's a very small portion of the atom itself. So it's also a very dense portion of the atom. We also then have the electron cloud, which contains the electrons, and this surrounds the nucleus. Remember that the electrons have a negative charge associated with them. The entire atom has a diameter about 2 to the minus 10th meters, which is about 200 picometers, or about 2 angstroms. So again, you can tell that most of the atom is actually empty space that is comprised of the electron cloud, which is the area where we are most likely to find the electrons. So with atomic structure, I also want to review some of the terminology that you should be familiar with. The first is going to be the atomic number, which is a capital Z for its symbol, and this represents the number of protons that we have in the nucleus of the atom. We also have the mass number, which is represented by a capital A, and this is the number of protons and neutrons in the nucleus of the atom. So we define the element by the number of protons that it has in the nucleus of the atom. If we change the number of protons, we would change the element type that we are looking at. But because of this, we also have isotopes. Isotopes are atoms that have the same Z, but they have a different A. So what that means is they have the same number of protons, so they're the same element, but they have a different mass because they have a different number of neutrons in the nucleus of the atom. So with our isotopes, we have a notation to represent the different isotopes that we can have for the different elements. For our notation, we'll use our element symbol, which is a capital X. We will then have a superscript of our A value, which would be the mass number, the number of protons and neutrons in the nucleus of that atom. And then as a subscript to the left, we would have our Z value. That Z value represents the number of protons that we would have in the nucleus of the atom. So if we look at a specific example of carbon, there are 3 different isotopes of carbon. We have carbon-12, carbon-13, and carbon-14. So I represent the carbon-12 isotope as carbon with a mass number of 12 and an atomic number of 6. I could then represent carbon-13 in the same fashion. So with both of these numbers, it will allow us to calculate the number of neutrons that we have in each atom. So carbon-12 has 6 neutrons, while carbon-13 has 7 neutrons in the nucleus of the atom. So these are 2 isotopes. Another way that we can do the notation is we can just show the notation with the mass number. So I could write carbon-12 with just a symbol of 12, or I could write carbon-13 with just a notation of 13. I do not have to show the atomic number because that atomic number is found on the periodic table. And as soon as we define that the atom is carbon, we have also defined exactly how many protons it has, and you could look that up directly on a periodic table. So these are 2 different ways that we can denote different isotopes. Atoms that have the same proton number, but they have a different mass number. With this information, we also have what we refer to as the atomic mass. The atomic mass is the weighted average of all the different isotopes associated with an element. So notice that we had 3 different isotopes associated with carbon, carbon-12, carbon-13, and carbon-14. So we can actually calculate the atomic mass, which would be the weighted average of all the isotopes of carbon. Those weighted averages are based on the abundances of each one of those isotopes that is found in nature. It is this atomic mass that is actually found on the periodic table, because any sample that we have would have that weighted average for the mass of the atoms within that sample. So we typically use atomic mass more than we would use specific isotope masses. We also have ions, and remember, ions are charged particles. We generate charged particles because the protons and the electrons are no longer equal. We either have more protons than we have electrons, or we have more electrons than we have protons. And that is what generates the charge for us. For our charges, we have an anion. Anions are negatively charged particles, and we create these negatively charged particles by gaining electrons. We also have cations, and these are positively charged particles, and we gain these positive charges by losing electrons. So what you want to remember is that we can only alter the electrons to generate our charged particles, because if we change the proton count, we change the atom type or the element type. So you want to make sure that you remember that we can only gain and lose electrons to generate our ions. With our atoms, we also have our atomic orbitals, and our atomic orbitals help us understand the shapes of atoms, and they also help us understand a little bit more about the electrons that are found in the electron cloud around the atom. So with our atomic orbitals, we have these wave functions. Psi is the abbreviation for our wave functions, and our wave functions are really what's going to represent the orbitals for us. And these are what's going to describe the behavior of an electron via mathematical equations. So electrons are in the electron cloud, and they are constantly moving in rapid random motion. So we really cannot pinpoint exactly where the electrons are because we know the motion associated with them. And due to the uncertainty principle, we cannot know both the location and the momentum of any particle. So what these wave functions allow us to do is they allow us to describe the electron via mathematical equations, and it's really Schrodinger's equation that all of this comes from. But where it becomes important for us is looking at the psi squared. The psi squared value describes the three-dimensional space around the nucleus that the electron is most likely to occupy. So this is what allows us to really kind of get an idea about where the electrons are most likely to be around the nucleus of the atom, which will help us understand our bonding, since it's the electrons that are involved in bonding itself. So with our orbitals, we're going to define the orbitals based on quantum numbers. So we have a few different quantum numbers that you'll want to remember from your freshman course. The first is our principal quantum number, which is abbreviated with a lowercase n, and this can be any positive integer, 1, 2, 3, 4, etc. And it really describes the energy and the size associated with the orbital. And remember, the orbital is the area we're most likely going to find the electron in. We also have the angular momentum quantum number, and its abbreviation is a lowercase l. And this value can be anywhere from 0 to n minus 1. So we need to know the n in order to know the l value. This l value is what's going to define the orbital shape for us, the three-dimensional space. We also have the magnetic quantum number, and its abbreviation is m with the subscript of a lowercase l. The ml value is going to be negative L to 0 to positive L and any integers in between. What the magnetic quantum number defines for us is the orientation in space. We also then have the spin quantum number. The spin quantum number's abbreviation is an m sub s, and it is either plus 1/2 or minus 1/2. And it really defines for us the spin on the electron. All the orbitals that have the same n value, we're going to say that they are in the same shell. So all of the orbitals with an n value equal to 2, we would say are in the second shell. All the orbitals with the same n and l value are considered to be in the same subshell. So if we have orbitals that have an n equals 2, or an n equals 3, and an l equals 2, we would say all of those orbitals are in the same subshell. So if you've forgotten anything about your atomic orbitals, you might want to do a quick review from your freshman course. But I do want to quickly review the orbital shapes because they will play a role again in some of our bonding patterns. So for our first shape, we have an L value equal to 0, and our shape is going to be a sphere for us. This is orbital type S. So when we look at this, this would be our orbital type S when L is equal to 0. To look at the ML values, remember ML values define our orientation in space. ML values have to be negative L to 0 to positive L. So we only have one ML value associated with the L equals 0, and that would be that ML equals 0 as well. So we only have one orientation in space for a sphere. And this would make sense. It is spherical. No matter how you orient it around the nucleus, it is occupying the same space. We then also have our L equal to 1. Our L equal to 1 shape is what we refer to as a dumbbell shape, and this is our p-type orbital. With our p-type orbital for our ML values, we have -1, 0, and +1 as our potential ML values. So what this tells us is that we have 3 orientations in space for this p-type orbital, or this dumbbell shape. So if you can think about this in terms of being on an x, y, and z axis, we would have one dumbbell that is on the y-axis, we would have one dumbbell that is on the x-axis, and then we can also put a third dumbbell on the z-axis, so it would be coming out at you and going back behind the screen of the page. So those are our 3 different orientations in space that we have for our p-type orbital. We also have our L equal to 2. Our L equal to 2 is what I oftentimes refer to as a double dumbbell, and this is really our D-type orbital. With our D-type orbital, our ML values are -2, -1, 0, +1, and +2. So we have 5 orientations that we can have in space for this double dumbbell. One of the other orientations in space is not actually a rotation of the double dumbbell that we see. One of the other orbital notations is to have a single dumbbell with a donut around the middle of it as well. So some of our orientations in space are not just rotations of the original shape, but they do become completely other areas where we're most likely to find electrons. So please remember that these shapes that we are defining are just areas around the nucleus of the atom where we are most likely to find electrons. We have one more orbital type that you want to be familiar with, and that is when our L is equal to 3. When our L is equal to 3, we have our F-type orbital. The most common notation for our F-type orbital is really 4 of the dumbbells all hooked together, so it kind of looks like a flower, which is one of the ways that I remember that it's the F-type orbital. With our F-type orbital, the ML values are -3, -2, -1, 0, +1, +2, and +3. So we actually have 7 orientations in space for our F-type orbital. For us, the ones we're going to be most concerned with are going to be the S and the P type subshells. Those are really the ones that are going to play a role in the reactivity and the orientation of our carbons and our hydrogens. So I also want to quickly review electron configuration. Remember, electron configuration is our notation that defines for us all of the electrons that are found around the nucleus of the atom and their location, so which orbitals they are found in. So with electron configurations, we are most often going to consider the ground state. The ground state is the lowest energy arrangement of all of the electrons. So the lowest energy orbitals are going to be filled first, and this is our Aufbau principle, which means when we start placing electrons into these orbital shapes, we're going to start with the lowest possible energy, and then we're going to fill outward to higher energy orbitals until we run out of electrons. Only 2 electrons can fit in one orbital, and they must have opposite spins. So one would be +1/2, one would be -1/2. And this is our Pauli exclusion principle. If we have degenerate orbitals, we're going to put 1 electron in each orbital before we go back and start to pair. This is Hund's rule. And what we mean by degenerate orbitals is we're really referring back to our subshells. So orbitals that all have the same L value. They all have the same energy. And that's what it means to be degenerate. Degenerate implies that there's the same energy. So anytime we have orbitals in the same subshell that have the same energy, we're going to put 1 electron in each before we go back and start to pair. Once we have our electron configuration, we can define the types of electrons we have. So one of the types of electrons are going to be valence electrons. These are going to be the electrons in the highest energy shell. These valence electrons are the ones that are going to be used in bonding. So they're the ones that we want to be easily able to define. We then also have core electrons, and core electrons are the electrons in lower energy shells. These shells are typically what we call full shells. So they're orbitals that all have the same N value, and all of the orbitals within that N value would have 2 pairs or 2 electrons in it, 1 pair of electrons. So let's review a couple of examples of electron configuration. So the first one that I want to look at is fluorine. And if you find fluorine on your periodic table, fluorine has a total of 9 electrons in it. So we're going to place all of those electrons in our orbitals. And we have to start at the lowest energy orbital, which is our 1s orbital. So fluorine's electron configuration would be 1s2, 2s2, 2p5. So if we look at this and we want to define the valence electrons, my valence electrons are the one in the outermost shell. So these would be my valence electrons that are in the 2 shell. So the 2s2 and the 2p5. So it would have a total of 7 valence electrons. Our core electrons would then be the ones in full shells. So for this example, it would be the 1s2. So we would have 2 core electrons in fluorine. One of the other things with this is our normal electron configuration. It shows all of the electrons and all of the shells and all of the orbitals. From this, we can also do our orbital diagram notation. With our orbital diagram notation, it actually shows us all the specific orbitals. Because if you'll notice in our electron configuration, we group subshells together. So remember, subshells come from the number of ML values that we have. So if we actually look at the orbital diagram notation, I have 1 orbital in the 1s subshell. I would have 1 orbital in the 2s subshell, but I would have 3 orbitals, 3 orientations in space in the 2p subshell. So it actually defines a little bit more about the pairing of our electrons when we look at this type of diagram. So in my 1s orbital, I have 2 electrons, and they would have opposite spins. We denote those spins by an up arrow and a down arrow. In the 2s orbital, I also have 2 electrons, so I would show the up and the down arrow. In the 2p subshell, I have to fill in 5 electrons. But remember Hund's rule. It tells me I have to put 1 electron in each of the orbitals before I go back and start to pair. So I would place 1, 2, 3, and then I would go back and start to pair for 4 and 5. So this notation would tell me that I have 1 unpaired electron in fluorine. And that will be important later on as we get ready to start looking at bonding. So now let's look at our example of chlorine. Chlorine on your periodic table has a total of 17 electrons around the nucleus of the atom. So normally, once again, we would want to start at our lowest energy level, which is the 1s2. But electron configurations can get very, very long if we have to start at the 1 point every single time. So we have what we call a shorthand notation for electron configuration. It may have also been referred to as an abbreviated electron configuration. There are a variety of different names used to represent this. But all it means is that we are going to start at the nearest noble gas of lower atomic number instead of starting at 1. So for chlorine, if you're looking at it on your periodic table, we can start at neon, which is the nearest noble gas, group 8A or 18, of lower atomic number. And then I'm going to start from there. So the rest of my electron configuration would then be 3s2, 3p5. So what this condensed electron configuration does for us is you'll notice it's only showing me my valence electrons. And once again, I have 7 valence electrons. All the core electrons are summarized by just stating neon. So once again, if I wanted to look at this in the terms of my orbital diagram notation, I would have 1 orbital in the 3s subshell. I would have 3 orbitals in the 3p subshell. And I can go through and I can actually see how many paired and unpaired electrons we have once again. So the last example that I want to look at is going to be antimony. And antimony has a total of 51 electrons around its nucleus. So to do an abbreviated or condensed electron configuration, I would be starting at krypton for my electron configuration. Then I would have 5s2, 4d10, and 5p3. What you want to remember with these is that where the D and where the F subshells fit in. Remember, the D is there where your transition metals are, and the F is at the block of the periodic table that is down beneath the main periodic table. So you want to make sure that you can fill these in. You also want to notice that they have a lower energy value, a lower principal quantum number, than what the S and the P values do. If we filled in an F, it would be 2 lower in the energy value than the S and the P orbitals as well. For my valence electrons, since that D subshell is full, we would not include the D subshell typically for valence electrons, as long as it is a full subshell. So my valence electrons here would once again be coming from the S and the P subshells. So we would have a total of 5 valence electrons. The core electrons would then be summed up by krypton and the 4d10. So please make sure that you do review your electron configuration if you have forgotten any of it from your freshman course.